Yeah, boundary algebra positroids. That's the name of the talk. This is joint with Christina, my advisor. Let's see. We're doing 3-step mathematics today. We're going to define the things that we need to define. It has quivers, I promise. We are going to compute some paths and relations, and then we're going to show that we've computed the right paths and relations. So, what's a dimer model? We're taking a quiver and we're embedding it into a disk. And it's important that we have clockwise faces and counterclockwise faces. All of our faces are clockwise or counterclockwise. We are considering our boundary vertices to be frozen. That's why they're boxes. It feels a bit sacrilegious to be drawing arrows between frozen vertices. The reason we're doing this is so that we can actually have our disk be the union of all our faces. So we call these arrows between frozen vertices boundary arrows, and we call the other ones internal arrows. We're doing representation theory. We want to make a path algebra with relations. And the relations that we have are anytime we have an internal arrow here, it's going to be a part of exactly 2 different faces. One of them is clockwise, one of them is counterclockwise. And so these give me 2 different return paths that go from the end of alpha back to the start of alpha. And I'm going to say that these are equivalent. These are the same path. And morally, I sort of think of this as, taking this path here and sort of morphing it along through alpha. There's actually a homotopy that you get to this path in the other direction. And we're going to use the word morphs for this. So the elements of our dimer algebra are going to be equivalence classes of paths under doing these basic morphs. Okay, so I was already drawn on this, I guess. We have a special type of path that exists in our dimer model. We call it a face path, which is just something that starts at a vertex and goes around one of our faces to get back to the same vertex. And any face path is the same. We can see by these dimer relations. If we take f to be the sum of all face paths, this actually commutes with all of our paths. And we can sort of see an example of that happening here. We start with the path on the left. And this path has this return path right here. I can switch it out for this one over here, which takes me to this middle path. And now I've created a new return path here. I can switch it out for this guy over here to get up to the right path. And the left looks like do a face path and then go along this arrow. And the right looks like go along this arrow and then do a face path. And in this way, you can sort of always draw a face path and morph it along your path until you get it to the end. And so doing a face path and then doing a path is always the same as doing that same path and then doing a face path. So this commutes with everything in some sense. We care about not all dimer models, only the very special ones. And to us, special means they have to be thin. We care about minimal paths, which are, for example, this purple path here. There's no way I can morph this at all. And this means it's minimal. Or generally, a minimal path is one that I cannot make into something that has a face path. So no matter how I do my morphs, I'm never going to be able to make a face path. And to call a dimer model thin, I want there to be, for any 2 vertices, a unique minimal path up to equivalence. And if I have any other path from those same vertices, I want to be able to morph it into a minimal path plus a bunch of face paths. So if we fix 2 vertices, our paths are really nice in this thin model. This path here is this dimer model here is a non-example because these purple and pink paths are between the same vertices, and I can't make one into the other plus some face paths. I don't like this dimer model, it's not thin. One reason we like thin paths is that they end up giving us cancellation algebras. This means that we can just cancel paths. I phrased this in terms of ideals here, but really this statement means that if If I have paths P and Q, and they compose with some path A, then PA is equal to QA if and only if P is equal to Q. And similarly, the same thing works with precomposition. So BP is equal to BQ if and only if P is equal to Q. If this is true, we call a path cancellative, or we call a path algebra with relations cancellative, or we call the ideal cancellative. And if we have any ideal that might not be cancellative, I can sort of take its closure with respect to this cancellative property, the smallest ideal containing it that is cancellative. Okay, this one's in the title. A boundary algebra is, we have some Deimer model and we're looking at the same relations, but we're only looking at the boundary paths now. So we're only looking at the paths that start and end at boundary vertices. And our Gabriel quiver is going to be a little bit messed up when we do this because, of course, we're removing all of the internal vertices. And the arrows of our Gabriel quiver are going to be the boundary paths such that no matter how I morph them, I can't make them go through any boundary vertices except for their start and end. Okay, we know enough to know what we would like to know. Thin Deimer models come from Postnikov diagrams, and these are associated with positroids. And something that was initially shown by Jensen, Kingsfield, and Bauer, King, Marsh for the Grassmannian case is that we can take the boundary algebra and we can complete it, and we can take the Gorenstein projective module category. And this gives us a nice additive categorification that sort of respects the frozen variable structure here of this, in this case, Grassmannian variety. And it was more recently shown by Pressland that we can do this for any positroid varieties, not just the really nice ones. Now, in the Grassmannian case, which we'll see a little bit later, we know what the boundary algebras look like. It's a nice circle quiver and simple relations. For the general case, it's not clear, and that's what we're trying to address here. We want to see what the more general ones look like, maybe find some formulas. Okay, so how are we going to get at boundary algebras of more general positroids? Well, it turns out they all sort of come from these things called lay diagrams. The setup for a lay diagram is I'm going to draw a Young tableau, and in some of the boxes, I'm going to draw a path all the way to the east and all the way to the south. Not going to do it in all of them, just in some of them. This is always what we call a lay diagram. We want nice lay diagrams where the boxes are not uber big. This box is too big because it hogs the boundary. It touches the boundary in more than just one place. Whereas in this model on the left, all of these only touch the boundary in one place, except for the top left box, which is always greedy. We can't do anything about that. So we like the one on the left. We don't like the one on the right. Some of these boxes are internal. Some of them are boundary. And when we turn this into a Deimer model, these are going to turn into our boundary and internal vertices. Now, there's a whole bunch of definition that's maybe a bit much to unpack, but I'll say a little bit here. If we have two boxes that are one above the other and they share a left boundary, we're going to see an up arrow. Similarly, we'll see a left arrow if they have the same top boundary. We ever have a sort of upper left corner here, we're going to see an upper left arrow. Down arrows are always between two boundary vertices that are on the right if they don't have the same left boundary here. Looks like this. Similarly, we get right arrows, and down right arrows are when we have this four corner sort of situation here. So, okay, we look at our lay diagram, we do some stuff, we get a Deimer model. We can say something very nice about this Deimer model setup. This is a perfect matching. I'm sort of saying that this arrow that I drew here is the down direction, and any arrow that goes in that direction is descending, and arrows that go in the opposite direction are ascending. And I'm making the observation here that every face of our Deimer model has exactly one descending arrow. This is a really nice property. So these dimer models are thin. And if we think about our dimer relations, we're always sort of substituting one return path for another. And since each face path only has exactly one descending arrow, this is going to preserve the number of descending arrows. And well, we're thin, so any path is equivalent to a minimal path plus some face paths. So this means that we can understand our path equivalence classes just by looking at descending arrows. So two paths are going to have the same number of descending arrows if and only if they are equivalent to each other. And the minimal path is the one with the least number of descending arrows. So we're going to use this to understand equivalence classes. I said a little bit earlier that we already understood the Grassmannian case. I'm going to say more about what this means now. So the Grassmannian case happens when we have a Ley diagram which is square and it has all of the possible lines drawn in. Now, in this case, to understand this, we're going to define xi and yi to be the paths going clockwise and counterclockwise, respectively, between our boundary vertices, which we're numbering clockwise. And well, I'm just going to draw what I call this circle quiver on the right here, which has a vertex for each boundary box and an arrow for my xi's and yi's. And I'm going to draw these relations here. This first one, x to the 5th equals y to the 6th. More generally, this is x to the width equals y to the height. And this just means that doing x 5 times is the same as doing y 6 times. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. These are the same. Xy equals yx. Again, we can see this quite simply on this dimer model. Doing x and then y is the same as doing y and then x. I think I drew those in the opposite order, but oh well. These are actually both base paths. And as we already know, base paths are always equivalent. So this one's not so bad. In the Grassmannian case, this is always what the boundary algebras look like. Now, something that was shown by Jonah Berggren is that even if our Ley diagram is more complicated, we can still do the same thing. We can still define our xi's and yi's as these minimal paths that are going clockwise and counterclockwise. And these same relations still hold. So we still have xy equals yx as space paths, and x to the k is still y to the n minus k. But of course, we're going to have more arrows potentially in this case. There's going to be more stuff going on. So we're going to call a pachinko arrow an arrow of the boundary algebra that is between non-adjacent vertices. So this is something that does not show up in this circle quiver that we drew a little bit earlier. And again, these come from boundary paths that I can't morph and make factor through an extra boundary vertex. So we're going to try to find these. The way we're going to do this is we're going to fix vertices v1 and v2. And rather than unpack those conditions I wrote, I'm just going to say it looks like this. I could also draw it so that v1 is sort of above and to the right of v2. This would be dual and everything is sort of the same. So we're going to say it looks like this. And first thing I'm going to do is I'm going to color some boxes. I'm going to color the box of v2 first, and then I'm going to go to the top left box, and I'm going to do it again and again and again until I've colored all these boxes, and I'm stopping when I'm above v1. Now, since I stopped above v1, I have a path from v1 to the last box I colored in that has no descending arrows. Now it turns out I have a path to the next colored box using exactly one descending arrow, and to the next and next and next. You unpack this, and this means that, that I have this path P from v1 to v2, and it has exactly 5 descending arrows, which is 1 less than the number of boxes that I drew. The observation is that this is the best we can do. For example, if I draw this little inner corner here, in order to enter this area from outside of it, I must use a descending arrow. Similarly, in order to enter this area or this area or this area, need to use a descending arrow to enter any of these areas, which means that any path from V1 to V2 must use at least 5 descending arrows. And well, hey, I already have a path that uses exactly 5. That means that this path has to be the minimal one. We can do a little bit better here. I can calculate the rightmost and leftmost paths. I'm going to start here. I'm going to go up. And what I would love is to enter this little corner here with a descending arrow. But right now I can't, because right now I'm in this box and it doesn't go far enough right. So I'm going to go up again. Now my box does go far enough right, which means I can go down into here. Well, now I want to enter into this next corner. And I can do so immediately because I'm already far enough right. You see the same case again. Not quite right there. Go down here. Well, now I'm in this box. I'm not far enough right to make it into this. So I have to go up. Now I'm far enough right again. I go down, and so on. That's much prettier. This is a rightmost path. And what that means is that any minimal path from V1 to V2 is going to be to the left of this path. I can do essentially the same thing and get a leftmost path. If I draw both of these, this means that the vertices that a minimal path from V1 to V2 could possibly factor through are just the vertices between these paths. And so I color in all these boxes. In particular, I colored in some boundary boxes, which means, well, we can make this minimal path factor through some extra stuff, and so it's not an arrow of boundary algebra. If none of these extra ones were boundary vertices, then this would define an arrow of the boundary algebra for us. And so we can use this to check if we have an arrow from V1 to V2. We can do a little bit more here. We can talk about some particular relations. Remember, these yi's are the arrows that go counterclockwise between adjacent boundary boxes. And each yi is either going to move right or it's going to move up. And I'm going to observe that the ones that move right always have 1 descending arrow, and the ones that move up always have 0 descending arrows, which means all I have to do to figure out how many descending arrows are in the composition of y's from V1 to V2 is just say how far apart are their x values. In this case, they're 8 columns apart. This means that the composition of y's has 8 descending arrows. So, okay, composition of y's has 8 descending arrows. P has 5. I'm going to subtract these numbers and get 3. This is the number of face paths that I have to add to P to get a composition of y's. And so we can compare our path to a path that we always know exists. And well, we're going to show that this is actually enough. So again, to sort of recap, given 2 vertices, I can check if there's an arrow in the boundary algebra between these 2 vertices, and I can compare it to a composition of y's. And so I'm going to draw a quiver, and I'm going to have, of course, a vertex for every boundary box, and I'm going to have arrows for my xi's and yi's. And I'm going to just add an arrow for all of these pachinko paths, all of these new paths between non-adjacent vertices that should be in there. And well, my relations are just going to be all the ones that I've talked about. We have these 2 types that we already know happen, these Grassmannian relations from the Grassmannian case. And for every pachinko path, we have this new type of relation that just looks like this path plus some face paths is the same as a composition of y's. And point is, this is enough. We need to take the cancellative closure of those relations that I just mentioned to get a path with relations that is cancellative. But once we do this, we actually get the boundary algebra. And the proof of this is really not so bad. We have these, well, we already know that these relations all hold. And so we just need to show that there aren't any extra relations in the boundary algebra that aren't in this. And if you did, you could assume it looked like P minus Q. And what you're going to do is you're just going to multiply it by an uber massive power of xy to the m so that you can take all of your p's in either side and turn them into x's and y's, and then you're done. So this is not so bad. Just a little example of what this sort of looks like. In this case, my new pachinko arrows are just these arrows from the inner corners to the top. And so I can just draw this circle quiver. I really should have drawn these. And I can label these arrows by how far are they from a composition of y's. And, oh, this gives me enough info. I can add these three relations and get the right thing. And okay, well, what might we do with this? In general, you can get some wacky stuff happening. And so in order to actually get nice characterizations, we need to restrict some special cases. But in special cases, we can actually use this to get characterizations. These are three examples that I won't go into because I think I'm pressed for time here. And well, again, just to say a little bit, what we are really interested in here is categorifications. That's why people care about boundary algebras. And so something that we would like to think about, but to some degree haven't, is, well, hey, what can we do with these Ornstein projective module categories? We would like to maybe use them to understand these module categories of the Grassmannian case that people already look at. How can we start doing this? This is something we would like to think about but haven't. That's about all I got. Thank you.
Questions from the audience? Could you go back to the slide of the theorem?
Sure.
So the QP is the original but there is additional arrow.
Yeah.
And the INP is the idea of the neutralization.
Yeah. So it's the ideal I've added in the Grassmannian relations, and I've also added in just one of these representatives for each pachinko path, and then I've taken a cancellative closure. So I'm taking the smallest ideal that's cancellative that contains this.
So I was wondering about the following. If you have say the positroid variety stratified,
Right.
if you have a positroid variety which covers another in the post set given by the stratification, so it's sort of as close to each other as possible.
Right.
Could you just, do you think it would be possible to describe some kind of basic move where you transform the boundary algebra of one into the boundary algebra of another? So you add some small pachinko path and then some relation, and then every time you go down a couple relation, you're adding some more pachinko paths or something like that.
Yeah, that's a good idea. I haven't thought about this. My first desire would be, so I don't know what this looks like in the lay diagram case, I guess. Do you know this? Like, in theory,
I couldn't say for sure, but it would be something like you remove the box from
yeah. In theory, like the lay diagrams ought to be quite similar. And so I think the way that you do this combinatorics and color the boxes and stuff is gonna obviously be quite similar, except for certain steps are gonna be a little bit different. You're gonna end up going further or not further when you do this setup. And so it should be quite similar. So my guess is, well, okay, this is probably a good idea. Probably. Hopefully say something, but I've not thought about this.
Can you say something about, I mean, it just seems to me kind of a funny thing to do, to take the vertices that I would have thought were the kind of the interesting vertices and throw them all away and just keep the vertices that I would have thought were not the interesting vertices. I mean, and, you know, kind of this criticism, I'm just sort of wondering why that's the right thing to do. Can you comment on that?
So your comment, you don't like that we're throwing away the internal vertices.
Yeah, I mean, it seems like I would have said the internal just very naively, I would have said the internal vertices was like the interesting stuff, and the boundary vertices was not the interesting stuff. And you're doing the opposite. So
yeah, I'm not really sure. So again, I mean, we're motivated by like this. We get a categorification by doing this. In some sense, like you want to get the information of the frozen vertices. I mean, as I understand it, the reason why we like these or a reason why we like these categorifications is because they're not like cluster categories, they're for BDS cluster categories. And so they have information about these frozen variables in there. And I don't know, you're still getting the information from these internal vertices, because if you take this category and you mod out, you mod out by the projectives, you're gonna get the cluster category with no frozen variables associated to just the internal part of the quiver. So I mean, you're still getting the information of the frozen vertices, or of the internal vertices somewhere in this boundary algebra. Somewhere this stuff is there, because it can come up again in the categorical picture just from the information of this boundary algebra. But not really. I don't have a sense for what we're doing when we're like removing these internal vertices, aside from the fact that like somehow we're really not losing their information completely.
Okay.
So maybe just a quick comment. Like the internal vertices somehow correspond to the semantic cluster tilting object, which might change because they're the non-projected indexes. And obviously the algebra which gives the cluster category, it doesn't depend on the individual cluster tilting objects in the category. So somehow the algebra which defines the cluster category is always the same, regardless of what the internal vertices are like. And the thing that's constant is the boundaries.
Okay.
Yeah.
Okay, so Keller wrote something that's very similar to what he said is the internal stuff is not unique. The boundary algebra is an invariant under mutation, in a complete invariant, in fact.
So I think he put it much better.
So, are there more questions? Maybe I have just a broad confirmation. I heard that the positroid actually these are part of the special case of the gray vertices. So gray vertices are kind of related to like random fields, right? So they are like each class, some cluster, they will give you a feeling of the leaf. So yeah, maybe there are some combinatorial way and from that.
Yeah, maybe. I hope. I'm not sure.
Okay, so yeah, let us end the speaker again.